Okay, so today our speaker is Alex Webb. See if I remember this. Alex is undergrad at Amherst, PhD UCLA, worked at LSU, then Leeds, and now here. That's it. Yeah. All right. So I made it on time to this talk, which is a plus. Okay, so we're going to talk about early tectonics on Earth and other planets. And these are the kind of questions we ask. What's striking about these questions is that there's no consensus answer. So last year we had a talk that went through a bunch of the models for these from Professor Zhao. And so I'm not going to dwell on that so much as to talk about another model. You know, when did plate tectonics start? How did plate tectonics start? What was before it? These are fundamental questions. These are like human evolution, human history, origin story questions. You know, it's long before us, but it's tied into the origin of life, and we don't know these. It's an exciting mystery. So you can see Max here pondering this, and thus you may be able to guess the next slide. Can anybody guess the words on the next slide? Anybody with young children know what's coming next? The basis of the model that I'm going to talk about next relies on the next page of this book. If you recognize this book. Oh, wait, I'm not even plugged in here. Here we go. It's not advancing. Ah, there we go. And it was still hot. So when Earth was young, it was hotter because we have most of our heat from radioactive decay. So it was something like 3 to 5 times hotter. And this is a reasonable basis for just simple, starting from the physics end of things, exploration of what early Earth may have been like. And so that's kind of where me and my colleagues have started. We started also from an observational basis that Hadean zircons appeared to be too cold, which would seem the opposite of too hot. But as you will see, too cold in the lithosphere matches up very well with too hot in the planet. For young terrestrial bodies. So this is Io on the left and Earth on the right, scaled similarly. Io is in fact only slightly larger than the moon, but it loses 40 times the amount of heat per unit area that Earth does. So if you want to wonder what a terrestrial body might act like, if it's much hotter, Io might be a good place to start. So what you're seeing is 5 images over 8 minutes from NASA's New Horizons probe, and it tracks volcanism at Io. If you fly by Io at any random time, you're pretty likely to see a volcano going on. That's how it loses its heat. And the consequences of that could be pretty profound, and we explore those consequences by rejiggering essentially the tectonic model for Io and applying it to Earth. So let's look at the tectonic model for Io. So Io is losing heat through volcanic heat advection, and thus mass and material is blasting out from partially molten mantle of Io, convecting mantle, blasting through the lithosphere. The heat is lost to space. The material lies down quickly. And you have about a 1 centimeter per year resurfacing rate as a global average. So 1 centimeter a year is 10 kilometers per million years. This is a plate tectonic rate of laying new material at the surface of Io. Io has a 50 kilometer thick lithosphere. So all of that new material gets laid down at the surface, and then more comes, and then more comes, and then more comes, and it's all coming from here, the material is. So it lays down, and it's much like Hawaii. You're laying down hot volcanic material, but then the heat is lost to space, and everything's pretty cold. And then more comes on top, and more comes on top, and more comes on top. The material, because it's coming from below, you haul it out from below. So you create a giant system of tectonic subsidence. So the whole lithosphere is descending down at the same rate that material is being piled at the surface of the lithosphere. And since that material is extremely cold, the material coming down is very, very cold. So the lithosphere is refrigerated on this planet that is losing 40 times the amount of heat that Earth is. So it's really a profoundly different parameter space to consider this lithosphere in. Something else that occurs is because this material is descending, but it's descending in an essentially spherical body, it must contract because you have to get to smaller and smaller spherical shells as you push that material down. So globally, there's contraction, and this results in 20-kilometer high mountains on the surface of a body that is only slightly larger than our moon. How would they support such high mountains? Because this lithosphere is super cold, so it's super strong. So my friend and collaborator, Bill Moore, thought to attempt to simulate this kind of tectonics for early Earth. And what Bill did is essentially took standard mantle convection code. You could say the Tectonics group is essentially industry standard. He took their code and he made one tweak. Anytime any melting occurred, he would immediately, in the next time step, remove that volume of melt and bring it up to the surface. And when that volume of melt comes up to the surface, whatever that volume is, it pushes everything else below it down. And if you do that switch, some pretty weird things happen. What you see here is 3 different types of the model with different Rayleigh numbers. Essentially, it's the amount of internal heating. So this is relatively cold, this is relatively hot, and this is very hot. And as you pull this material up, in a very hot model, you produce a ton of melt. So you put a ton of material at the surface. So you're really rapidly pushing a lot of things down. Now it is volcanism, so it's kind of episodic and spatially heterogeneous. So you get a pretty bumpy base of your lithosphere as things are trying to heat up from below, but conduction is not getting much of a chance to warm this lithosphere, not compared to the downwards advection of cold material. So the downwards advection of cold material is mostly running the show here until you have a really sharp thermal transition at the base. And the cooler the planet is, the less voluminous the volcanism, the slower the push down, and the more conduction can flatten the base of the lithosphere. And this is an illustration that is kind of a pain in the butt to look at, but all it is geothermal gradient. So you're looking at depth or pressure as your y-axis, and you're looking at temperature as your x-axis. 1 centimeter per year, the blue lines represent Eo's rate of volcanic resurfacing. So a very, very rapid rate of volcanic resurfacing. And these are an order of magnitude less and an order of magnitude less. 3 arbitrary depths are chosen for the base of the lithosphere. So that's why there's 3 curves for each resurfacing rate. And all it's really showing is that the geothermal gradient of such a planet is super freaking weird. The geothermal gradient, a normal geothermal gradient today goes something like this. These geothermal gradients are carrying surface temperatures from the surface all the way down with no change until the very base of the lithosphere at Eo's rate, and with very, very little change at an order of magnitude less, and substantial change at 2 orders of magnitude less. So what you're seeing here is advection of cold surface materials dominating the lithospheric thermal profile. And here is sort of a mixture of that advection chilling the lithosphere and conduction warming the lithosphere, conduction from the mantle below. And this is sort of an illustration of how that could work through time. So your x-axis is non-dimensional time moving forward to the right. Your y-axis is heat flux or heat production. So the red line essentially shows you radioactive decay in the Earth. And as time moves forward, we expect radioactive decay to diminish as we have less and less radioactive material. That will translate into heat production and heat loss via volcanism in blue and via conduction in black. Now the first part of the model is just the model equilibrating itself. We can essentially forget this part. Once we get to here, we're in business. So here you can see that even background volcanism is dominating over conduction, and you have spike events of volcanism that are major heat loss events. It's a log scale, but eventually conduction starts to take over, And then in some way, shape, or form, we envision overcoming the strength of the lithosphere. We can talk about that more later, at which point you initiate plate tectonics. So the model predictions from this geodynamic work is rapid volcanic resurfacing, a low geothermal gradient, contractional deformation. Maybe we would see it, maybe we wouldn't, because Earth's lithosphere, the proportion of the radius of Earth's lithosphere is so much smaller than the proportion of the radius that Eo's lithosphere represents. And a rapid decrease in volcanism after the initiation of plate tectonics. My participation was to think that Bill's model would actually apply for much more than just the Hadean zircon, but potentially also for a substantial fraction of the Archean. So the three key places we looked in the Archean are the best preserved Archean terrains older than 3.2 billion years ago: Barberton, Pilbara, and Ishua. And Barberton and Pilbara are really the best preserved. So we look at those and we see an extremely simple geological pattern. This is a map of Barberton. You're going to have to trust me because it's hard to read this and know what these things are. It's easier to look at the Pilbara one. Let me just tell you, they're pretty much identical. And the Pilbara part that matters is the East Pilbara Craton, which is the Christmas part over here, red and green. So what you see here, I can show you a much more complicated map of this area, something with 30-40 units. But that all boil down to 2 basic units and 2 minor units. The 2 basic units are well represented here. You have mafic and ultramafic volcanic rocks, and you have the TTG suite, tonalites, trondhjemites, granodiorites in red. So mafic and ultramafic rocks in green, tonalites, trondhjemites, granodiorites in red. The tonalites, trondhjemites, granodiorites are, in my mind, not actually all that different because they represent melts of the mafic volcanic rocks. So since all you need to produce the TTGs is a bit of heat and wet mafic volcanic rocks, it represents the same protolith in a sense. So those 2 dominate the signal, and they're essentially almost the same source. Besides those 2, you have a little bit of material precipitating out of the ocean, things like this, and you have a little bit of locally derived plastic sediment, i.e. take all of the other rocks, and sometimes you get some local surface sediment comprised of those rocks. One other very minor component is periodically you'll get melts of the TTGs producing granite stencil. But that's it. And that is all that you ever see for protolith lithologies in any terrain that we have older than 3.2 billion years ago. So very few of us look at our geological records and think to ourselves, oh, this is super simple, right? We go out and we collect a suite of rocks, and whatever the heck it is, it's hard to us, right? There's a lot we got to interpret, there's a lot we got to do. We got to slice up the thin sections, figure out all the minerals, etc. It's always challenging to us. But from the perspective of everything else that we do in earth science, actually the Archean record is stupid simple. It is astonishingly simple. Mafic volcanic rocks, melts thereof, a little bit of ocean sediment, and a little bit of sediment coming from all the other rocks, and that is it. That's the entirety of the record in terms of protoliths. It's profound. What about Ishua? We focus on Ishua, it's a little bit older than the other ones. The other ones are 3.5 to 3.2. Ishua goes 3.8 to 3.6. There's another distinction about Ishua. So here, I can take you through it a little bit. 3.7 tonalite, 3.7 supercrustal rocks in green, 3.8 supercrustal rocks in blue, and 3.8 tonalite here. So the supercrustal rocks are mostly mafic volcanics, also some felsic volcanics akin to the TTGs, and some big. This is a view of the far northeastern end of Ishua here. It's kind of a neat place to go because the far northeastern end is surrounded by the Greenland ice sheet here. So it's kind of a cool view. This is a view from a helicopter. We're not on a hill. And we'll talk about the structure in a bit. You can see it's in southwest Greenland. So Ishua is a little bit extra interesting in the sense that the other terrains have been thought to represent a certain type of dome and keel structural formation that is largely interpreted via non-plate tectonics, via some kind of a stagnant lid type model, maybe with plume involvement, etc. Ishua has been exclusively interpreted until some of our work this year as plate tectonic. So the two models are highly different in the sense that they have different vergence in present coordinates. And one model treats the supercrustal rocks as a accretionary prism. The other model treats the supercrustal rocks as arc sequences. But nonetheless, it's all of the prior models for the Ishua supercrustal belt involve preservation along the length of the belt of a subduction zone or a collisional zone. So we didn't necessarily think that was going to be the case, so we went and looked. So this is our team for the 2017 adventure. We hope to do another trip this coming summer, so in 2021. And you can see how we get around. You get in with a helicopter, you got to walk a lot, you got to suffer the snow in July. We brought some inflatable kayaks, which helped us expand our range a little bit. And we couldn't find our lighters. And then realized that there were lighters built into the stove. Holy crap, we were so relieved. Not my proudest moment. So that is a moment of great relief. All right, so here's the sort of thing we saw there. There's supposed to be low deformation domains in Ishua, represented by a pillow lava. So you can see here the outline of a pillow, other pillows. This is one of the classical sites there where you can really identify in the mafic lavas that these must have been submarine lavas because there are pillows. And they're a big squeeze, but this is thought to be low deformation. However, you look at that same outcrop from other angles, you realize it's just as foliated and lineated as any other rock there. You just happen to have a good view direction. And so I think there's been a little bit of a misdiagnosis of low strain and high strain domains here. The whole thing is high strain. Similarly, the model for an accretionary prism, those guys posit that there's a metamorphic gradient across the belt, such that in the far northeast, there's no garnet. It's just lower grade, lower temperature. So this is simply showing that in the far northeast, there is indeed abundant garnet. And it's the same grade. The only thing that is different is that there's a lot more retrogression. So it's not a prograde signal that's different. It's a later retrogression that is a little bit more concentrated in the far northeast. Here's another shot of some beautiful pillows here. And this is one look at that outcrop where the pillows are spectacularly preserved and thought to be low strain. This is another look at the same outcrop from the side where you see just thorough beating of these rocks via stretching. They're thoroughly lineated and foliated. And you would never see the pillows. If you're looking at this rock, this very same thing, which is essentially the surface that's lit up right there, you look at it from the side, you're never going to see these pillows. Another aspect that we noticed was that there's a lot of funky folding, including what we interpret as sheath and curtain folds. This is not entirely new. Some previous groups saw some sheath folds there too. We also see multiple senses of shear. There's one dominant stretching lineation going steeply to the southeast, but the shear sense seems to be randomly distributed throughout the belt, such that it's either down to the southeast or up to the northwest, but no spatial coherence to it. So what we plot here in this stereo plot, which I'm sure some of you probably haven't looked at in a while and some of you are very familiar with, we plot all of the stretching lineations. In this red bullseye, we plot a bunch of fold axes in the black dots. So when the fold axes are aligned with the stretching lineations, that's a good indication of A-type folding. And then the interesting thing we did was we looked at each 3 kilometer long approximately panel of the entire arcuate belt and just plot those up there as the great circles. And those all intersect the stretching lineations also, which is another indication that the whole thing might be actually in this A-type style folding. So it's potentially Earth's largest sheath fold, which could tell us something quite dramatic about how the early lithosphere behaved. Because there's reasonable reason from prior work to think that most of the deformation was finished by about 3.6 billion years ago. So if it is a huge sheath fold, it's a huge ancient sheath fold. So this is a illustration of what a sheath fold, how a sheath fold develops. It develops kind of like a normal fold, but then some three-dimensional aspects get away from it, and it starts to bulge out like the sheath of a sword. So the model that we came up with for this is dependent on the idea that there is a lot of strain and a lot of thinning in this package of rocks. So we deposit the 3.8s. With that deposition, some material is pushed down, creates some partial melting in the underlying matrix volcanics. That produces a tonalite. Then nothing much happens for about 100 million years. Then you have another volcanic event, and you push everything down, create more melting, and intrude at roughly the same crustal level. So far, this is extremely similar to Barberton and Pilbara, with the exception that the sequences are thicker. The volcanic sequences are thicker, such that when you intrude tonalite, it doesn't re-intrude the same tonalite, because that same tonalite is pushed down so far, it goes right past it and goes higher. But otherwise, it's very similar to Barberton and Pilbara's type of geology. And then subsequently, everything gets really strongly deformed. Whether that is a plate tectonic event or shortening in a heat pipe context, we haven't yet deduced. But there seems to be a very strong deformation that creates the sheath folding. And also, other records in this area of Ocelli and other flattening indicators suggest that you've got something like a 90% flattening. So if you have a 90% flattening, it can get you from this thick crust down to this very thin preservation of the belt and the kind of sheath and curtain folds that we illustrate in this model here. So the point is not that the model is correct. Of course, it's wrong, but it is apparently viable for now. And it's very different from the prior plate tectonic models. And if anything is the theme of this talk, it's that. The early Earth is very simple, has very simple pearlite lithologies, relatively little preservation, so there's not a lot of degrees of freedom to play with. And there are a lot of models that can fit the record, that are viable, beyond what we are currently largely discussing. We need to imagine more, essentially. So the next part of this talk, we're going to talk about thinking about the same concept for other planets. Because if heat pipe cooling could be generally working on Io, and it might have worked on early Earth, then we wonder if it could be a universal process for terrestrial planets generally. So we're going to look at the other planets, and most of my prep for this talk involved showing you the people involved, because this is my home institution. I can be a little more free. So this is the team involved in this one. Before we worked on this stuff, we worked on a team triathlon together. I was the swim, Bill Moore was the bike, the geodynamicist you guys met earlier, and Justin Simon, who's a NASA geochemist now, was our runner. And we came in second by about 5 seconds. We didn't know the other team existed. Don't play. All right, so what are planetary surfaces made of? Let's think about those predictions we looked at earlier. Well, this is Io, and a different perspective, so you can see the volcanic centers all over it. You might be able to make out some of those mountain belts. Obviously, this is all volcanic material. Earth, actually, there's a fair amount of stuff that is not lava, but it's still mostly lava. The moon is all lava. You're going to sense a theme here. Very little lava. Sorry to the Mars people. Venus, lava and deformed lava. Mercury. So all of the rocky terrestrial bodies we have in our solar system are dominated by low slope, mafic to ultramafic volcanic lava. Oh, sorry about that. We can't usually tell the source except for the very late features. So if we compare this to our predictions that we had from the basic modeling, rapid volcanic resurfacing is a pretty easy match. Low geothermal gradient across the bulk of the well, how are we going to tell? Contractional deformation, yes. To the extent that we see much deformation, there is a possibilities of large-scale contractional deformation, and there is definitely some very minor extensional deformation that is usually associated with local features. So for instance, on Venus, you have extensional deformation accomplishing less than 1% of extension and associated with the volcanic edifices above plumes. Now, a rapid decrease in volcanism after the initiation of plate tectonics is thought not to apply to any of the other terrestrial planets, but what it does is it sets up a different prediction. Since that won't work, that would mean that for this model to apply to the other planets, you'd need to be preserving the heat pipe lithosphere. And that's actually a profound prediction, which has a lot of consequences. So we're going to look at those consequences. So this thick lithosphere, we would imagine through time, would be hotter, then a little cooler, then a little cooler, but at some point in the game, you're not going to be able to keep processing that much volcanism, and it might just slide into a stagnant lid. So let's look at how that would work. These are the two dominant models for how stagnant lid planets work. You either have a heat pipe system, or you have a rigid lid planet that cools mostly via conduction. Now, if conduction is your dominant heat loss mechanism, the hotter it is, the more heat it's got to lose, the thinner the lithosphere must be to allow a lot of heat loss. So if you think about Earth today, most of our heat loss is through the thin lithosphere near the mid-ocean ridges, because that's where it's easiest to escape. So if we need to lose a ton of heat from a rigid lid, stagnant lid planet, and we're going to do it via conduction, that stagnant lid has got to be thin, and it will thicken with time. So this is plotting lithosphere thickness against time. For a standard stagnant lid, it's just going to thicken with time, become thicker and thicker and thicker until it's essentially a dead planet. Heat pipe, as we've already seen, works pretty differently. So with heat pipe, since you're losing the heat via volcanic advection, you're piling up a ton of material at the surface, building a hugely thick lithosphere. And the slower you're losing heat, the slower you're pushing down cold lithosphere, the thinner the lithosphere can become. So a heat pipe lithosphere starts incredibly thick, thins with time, until it eventually simply becomes a stagnant lithosphere. Once it's no longer producing enough volcanics to be any different from just conductive cooling, then it's essentially a stagnant lid planet. So I think this text is a little redundant. We've already sort of talked about this. So, so let's look at this prediction versus the other terrestrial bodies in the solar system. And we can just look at their shape. So the moon is shaped like a lemon. It's kind of weird, but it's true. It doesn't have the shape that we would expect with a synchronous rotator at its current distance. It's not in hydrostatic equilibrium. Instead, it's a little warped. Now, we know how to make this shape. When the moon was younger, it was closer to Earth, it would be whipping around faster, would have more of that warped shape. So we know it's an early shape. The question is not how to make it, the question is how to preserve it. How do you manage to keep that shape through time? Mercury is similar. Mercury has a 3-2 resonance that must be supported by some kind of a permanent asymmetry. So it's a 3-2 resonance in its orbit. That's got to be a pretty major feature that should be equilibrated out. And the only way to maintain it is to have some kind of strength to maintain that early feature. Mars, so this is for the Mars folks interested in your opinion. You've got the hemispheric dichotomy. There's a fair amount of different models to form it. So Mars has these northern lowlands and southern highlands. Forming it is probably some sort of an impact process, or there's a variety of different possibilities. All of them are early. It is a very ancient feature of Mars to have this hemispheric dichotomy. And the question is not how to form it, the question is how to keep it. So all of these terrestrial planets are showing ancient topography supported by lithospheric stresses. The fact that this topography has not relaxed suggests that you have had throughout the history of these planets a cold, thick, strong lithosphere to support it. So this is quite supportive of the idea that the early path was thick and never got all that thin and transferred into stagnant lid, as opposed to starting very thin, which couldn't support any of this topography, and then slowly thickening with time. Large terrestrial exoplanets are worth a couple seconds of our time because if they're significantly larger than Earth, they're going to retain heat better. If they retain heat better, they'll cool slower. They might actually be in heat pipe mode for longer. So super Earth might not be the way we want to call them. They may actually, in fact, be super EOs. They may still be cooling in this kind of a mode and not in plate tectonic or stagnant lid mode. And that might last for the duration of their star's lifespan. So we proposed a kind of general model for terrestrial planets on the basis that we've been talking about so far, which is that you start with magma ocean, and then very rapidly after you can have enough rock bergs and they stabilize enough to form some kind of a shell, that shell is just going to be blasted through with volcanism, and you almost instantaneously get into heat pipe mode. Once you're into heat pipe mode, your path is either to stay there for the duration of the sun's lifespan, or transfer into plate tectonics, or directly into stagnant lid. And then in the long run, we're all dead planets, unless the sun explodes first. So this is our kind of general model. It's quite cartoony, but it's a fun conceptual distinction from things like Taylor and McLennan, the classical models of terrestrial planet development, which consider each of the terrestrial bodies in the solar system as almost completely stochastically developed. So it almost random chance what you get. This suggests it's much more systematic. We asleep yet? It can be hard. At least we don't give out cookies here. When I was a graduate student, they gave out cookies before the 4 p.m. seminar, and when it hit 4:30, I was down. So let's talk the last section. We only have about 10 slides left. So the last section, I want to talk about how plates broke. So how we get out of heat pipe and into plate tectonics. There's a variety of models for this. So you can have an impactor. So this little ball up here, where would represent some sort of an impacting asteroid or something that could mess with processes enough to initiate subduction. Potentially the lithosphere accumulates damage through time. So as mantle convection is applied to the base of the stagnant lid, it will push things around a little bit. You'll progressively build damage. And if some of those damage zones end up connecting enough, maybe you initiate subduction. Other possibilities is that there's different compositions of lithosphere, portions of essentially proto-oceanic and proto-continental lithosphere. And with them weighted slightly differently, things could start flowing laterally and initiate subduction that way. That's essentially what this Rayall model is. Or potentially a plume does a similar thing. So a plume might weight the lithosphere by applying a lot of new material at the surface, and with this different weight distribution, maybe you can overcome the strength of the lithosphere and initiate an annulus of subduction propagating away from the plume head. Our model is fairly substantially different. Essentially, all of these models are, the geodynamic coding of these models is all tuned to the dimensionality of plate tectonics and does not manage to get anywhere close to rock mechanics properties, which is fine because that's true for subduction zones today. Rock mechanics of subduction zones today, the strength of subduction zones is super low compared to what you'll get in a rock mechanics lab. So that's consistent with our understanding of ongoing plate tectonics. But nonetheless, Tom Chinon showed up in my office a couple of years ago he has a lot of ideas, but my sense was that I could make one of them potentially work via thinking of warming the lithosphere at the end of a heat pipe period, and what that could do in terms of thermal expansion. So what we've explored together is a heat pipe lithosphere towards the end of heat pipe mode is going to warm up. We saw that in the modeling we looked at earlier. And if it warms up, it will experience a measure of thermal expansion. And if that lithosphere, is a heat pipe lithosphere, and it's something like 60, 70, 80 kilometers thick. The thermal expansion should be, if it's rapid, that should be about a kilometer. And that's enough to crack it. That's enough to overcome the tensile strength of the rocks. Sorry, I misspoke. The speed doesn't really actually matter. So what we're showing in these models here is simply taking a shell with standard rock mechanics properties and pushing from below to about 3 kilometers, but the cracking occurs, and this is the reference model, at about a kilometer's worth of push. So that's about as much thermal expansion as you're going to get. And you can see the stress builds up, the tensile stress builds up, and then is relieved very rapidly by the rapid development of a crack network. So a little bit of fracturing represents overcoming the strength of the rocks because it's just expanding too much, it's been pushed too much, it's been stretched too much, and they break. If it breaks, it may continue to break. There may be a rapid coalescence of these fracture networks, and all of a sudden, you have a plate tectonic network dominated entirely by rifts. And if you have it entirely by rifts, this gets silly in a hurry, right? Well, this is the same thing, except in a rotating reference frame on the left. But what's that? So we know that this is essentially a modern day expanding earth hypothesis, which is slightly ridiculous. But the amount of expansion is so much less. Just about a kilometer is what you're going to need. So it is, mechanically viable and uses real rock mechanics properties as opposed to, having to tune to the scale of the plates. So let me show you a little bit more of the details. As we discussed, since these plots represent a heat pipe lithosphere at different internal heating, such that this is really hot, this is cooler, this is cooler, this material is going to thin to that, is going to thin to that if we think of this temporally in a cooling planet. Which means that since this is all lithosphere at this point, a lot of it's going to warm up pretty dramatically. So another way to say that is you're going to move from soliduses like this towards soliduses like this towards something like a modern solidus. That's going to drive a lot of thermal expansion, which we model simply as a push from below on a shell, and we watch that shell break at about the limit of the thermal expansion for an 80-kilometer lithosphere. And that's pretty much all it is. It is pretty profoundly different from the other models I showed you earlier, but one thing that it really has in common is this does not get you to subduction. What it does do, however, is when you have these fracture networks, like in the other models, now you have an easy conduit for melting to the surface, particularly like the Garia model. So with a bunch of easy conduits for melts to rise to the surface, you will differentially load the lithosphere along some of these rift margins, and then it's a fairly easy step to envision the initiation of subduction. And once you have subduction, then it can be a self-sustaining system. So it's similar to the other models that we've looked at so far. It's got to be wrong, but it's currently viable, and it's completely different from what we talked about earlier. This is an illustration of some of the parameter space. So here we're looking at the reference model, and you see time. Now the loading is at a constant rate, so very rapidly you all of a sudden develop a ton of fractures. So this is the fractures, and this is the total fracture network. So the red histogram with this peak here shows the amount of fractures developed in a particular period of time. So you have an explosion of fracture growth, and then that rapidly decays once you get a global network, and you don't have much fracture growth subsequently. So this is that rapid growth of the global network. The dashed line shows you the thermal expansion limit. So essentially, this is as much thermal expansion as we actually expect. We don't expect this much. So, but once you've got this much in the reference model, you have a global rift network. So it's enough. If you get smaller, then what you'll see here is we're looking at models from 20 to 200 kilometers thick. So we're just looking at this curve, at the total fracture length curve. And you can see that for 20, 40, 60, using standard rock mechanics properties, it's not thick enough, you don't have enough thermal expansion, it doesn't rift. The thermal expansion limit is here and back here. For the reference model at 80 kilometers thick, you have enough thermal expansion to rift, and similarly for the 100, 120, and 200 kilometer thick lithospheres. There's enough thermal expansion to expect that this rifting process will occur. And you know, if it's anything like Berkovicki's model applies, where there's damage zones, then the strength of the lithosphere is significantly less than standard rock mechanics properties, in which case maybe some of these could actually occur. Maybe the thinner lithospheres could also rift. Right, so a few coming attractions. This is one paper that Xiaowei is working on. He submitted once, we're going to resubmit again soon. He's looking at detrital zircon records for rocks deposited in the Archean and noting that they look fairly substantially different from 3.8 to 3.4 versus subsequent periods, suggesting a tectonic transition at this time. So essentially you're looking at the age of the zircons versus the age of the deposition. And for very old rocks, the age of deposition is almost the exact same thing as the age of crystallization in the bulk of sediments. But the younger you get, the more it looks like plate tectonics, where you can have substantially older zircons deposited into basins because you have a greater rock diversity at the surface. And Jupiter, who's now a PhD student at Georgia, at University of Georgia, she and a student here, Jason, are working on the margins of Venus's highlands because if the heat pipe model is going to apply to Venus, then the tectonic highlands of Venus, not the volcanic ones, but the tectonic ones, would be likely to be analogs to Eo's large mountains. And if that's true, then there's a simple prediction. They must have very old faults bounding those blocks. They can't be relatively recent features. So we're exploring the edges of those blocks to try and ensure that none of those blocks are bound by young faults. Thus far, so good. There's something else about Jupiter's work. You can see where these t-shirts of ours come from. So you may see us running around periodically with these t-shirts. Now you know where they come from. They come, so eventually this is going to be relevant whenever we actually get this published. This is a polar coordinate view of Ishtar Terra, which is the highest, biggest mountain system on Venus near the North Pole. And so that's what we made into our t-shirt. So to start summing things up, the questions we've been asking in this talk and addressing and saying that, you know, there's more models that could apply are these. And so if you're interested in particular of these questions, these are the papers to find our ideas in. I guess you can read that for yourself, so I won't belabor the point. To sum up, we explore early Earth and its neighboring terrestrial bodies. We're trying to figure out if there is anything like a generalized model for terrestrial planet development. We propose one, that heat pipe cooling might be a nearly universal phase in the transition from magma ocean to either plate tectonic lids or stagnant lids. And in this view, early Earth looks increasingly similar to other terrestrial bodies because all of them would be preserving heat pipe tectonics. Life would be developing in that period on Earth, again, if that's true, which makes it slightly potentially higher odds for life elsewhere. And if we follow that line of logic a little bit more, then we think, holy crap, we should fund the early Earth people because they're so much cheaper than rovers. So much cheaper than rovers. Okay, now there's one last thing I'm going to do because I never get to do this. The students always do this. I'm a little jealous. I get to show pictures of people. I like that. I think it's fun. So these are pictures of sort of science friends. Some of these people are collaborators. Most of them are not, but they're just friends. You may see yourself, you may not. Maybe you're not a friend. Well, Ryan. I don't know, Ryan is on here. Ryan is actually on the collaborator slide. So this is mostly collaborators. And again, it's a little mixed up. There's some students and people and And I don't know. I don't trust that guy either. And finally, and most importantly, students. So these are sort of my thank you slides. So thank you guys. We have a foundation of my earlier generation of students from Louisiana State University, mostly at the base, and then students here in the top and middle. All right, so if you have more questions, I'm really happy to hear, or any questions. Thank you very much.
Okay, very good talk. Hey, the plate breaking.
Why plate breaking doesn't happen on EO? Good question. EO is fundamentally different in that it is not cooling. Its heat source is not, it's not dominated by radioactivity in the slightest. It's by orbital dynamics. So EO is in a 1-2-4 resonance with two other of the Galilean satellites whipping around Jupiter. So Jupiter's a huge mass. The other Galilean satellites are pretty big masses. They're all tugging on each other. So this creates a ton of frictional heating. So it's essentially like warming up your hands like this. EO is never cooling because it's constantly doing this. So it's constantly warm. Essentially, the sun is more like is likely to explode before that orbital dynamics breaks down. So it's likely to maintain itself, yeah, for the duration of our solar system.
Okay, can you show your slide with pad?
So just tell me when you want to stop. We'll find some.
Yeah.
I'm trying here. Sorry.
Yeah.
Okay.
So watching the rocks, the melting, the lava, the composition, the melting some terrestrial.
In this model, there's no differentiation. It's all the same material. In reality, we know that it's large batch melting. You're putting up melts that are mafic, that are somewhat separated from mantle composition, but not too strongly. It's all mafic and ultramafic. And then as that descends, and a lot of that is wet, because a lot of it's pillow lava, it's trapped a fair amount of water. A lot of the wet descending melts remelt, or wet descending material remelts, and that is again a differentiation process that separates out the tonalite, transmite, granite, diorite from the original wet mafic rock. So there's steps that are leading us to some differentiation, more felsic material. Something I would point out before you maybe go there, and that is a very common question, particularly from the Nick Arndts of the world, is what about water? Yeah. Do you have enough water? And so the water question is really interesting in the sense that subduction sets up a continual conveyor belt of water, and you're continually bringing water down and melting the mantle ledge above it. So you have the mantle ledge sitting there, perhaps getting more refractory because it keeps melting, but you keep pumping water into it. However, the geochemistry of the rocks that we see does not match that at all. The geochemistry of the rocks that we see, for people that advocate subduction tectonics, they advocate slab melting in the Archean. They do not advocate mantle wedge melting, they advocate slab melting. So what they're advocating is taking a slab, putting it down, and melting it with its own water and own material. So you can take that down to the subduction zone if you want to, and it brings the amount of water it has and melts, and up it goes. Or you can just take it vertically if you want to. Brings the amount of water it has, melts, and goes. It's the same budget. We do not have a difference in water budget between this heat pipe descent and slab melting, because we're not funneling water into one place above and slab melting. We are simply melting the water we bring with us. Okay, so the water budget is the same. Whether it's a problem or not, I don't know, but it's the same as what's proposed for all models.
Just on that point with your expanding Earth for your how does this affect bringing water down? Or how is happening with the water relate to?
You mean the catastrophe of rapid rift element?
Yeah.
I have never thought of that. I don't know. It's a great question. I assume if the model is at all. So what my comment on Twitter when I announced this paper was that this is either heading for the textbooks or the dustbin, and it should rapidly go to either one of them, right? The question would be, is this worth thinking about to that level of detail or not? It might be. this might be exactly how plates broke on Earth. If we can deduce relatively rapidly, and maybe we can, that this is utter nonsense, don't bother with the question. So I don't know yet. It's a good question. I'm not sure if we will kill this model first before somebody gets to it seriously.
So that tectonic pattern, when the surface is covered by water, at that time the ocean already developed or not?
From the from the rock record, it would have to be, right? Because we see so much pillow web. It doesn't mean that everything is always covered in water, but it means there's substantial water at the surface in most of the records we have. There is always the question of preservation bias, but the funny thing about Archean terrains is, you still have, I don't know, you probably know better than me, maybe 10 or 15 or 20 terrains or fragments of terrains older than 3.2, and they all have the same protoliths. Whether or not they're totally deformed or not, high grade, low grade, whatever, that's always the same protoliths. It's scattered around the world. So that is something of an argument that the preservation is actually representative. It might not be, but it could be. In which case, it's a very simple risk. And
if in the surface, covered by the water, when the lava, erupted, the lava cell interact with the water, you can cause autolysis. And it can provide some water, or part of melting, right?
yes. Yeah, a lot of that water gets trapped in. And I think that's the same in any model. I don't really think there's a water budget difference in any of these models, which I definitely think people are confused about. And we should probably emphasize it more. Any other questions? Are there any questions on Zoom? Does anybody have access to Zoom or in such a way that they can set up these questions? I always mess that up. But if anybody has a question in the meantime, sorry, Cody, yeah?
Yeah, for you, I guess, is it the gravitational pull that might be driving volcanism?
It's the EO's volcanism is driven by heat. EO's heat is produced by the orbital dynamics flexing these lithospheres, flexing these mantles, creating frictional, essentially, if things are flexing, they're moving by each other. There's constant shear heat. Yeah, sorry, tidal, yeah, it's exactly. I'm failing to use the word tide, but it's a rock tide that's creating frictional heat. Thank you.
Are there any questions on Zoom?
Did you
Go to the mic or just type it in, that's all fine.
Did you have a question in the meantime, Sean?
Yeah. Sorry, okay, but you talk about super hot a lot in the Archean, but is your model account for perhaps in the Haitian, perhaps there was more chromatites than we imagine, flowing faster than water, the higher the temperature, so like the substance in water.
We don't get that specific.
Oh.
We just pile up mafic and ultramafic volcanics at the surface, and are not at that level of specificity. There is a potential. It's argued that chromatites might actually, well, the rock record is so fragmentary, it's hard to know, but there aren't necessarily any chromatites at Ishwa. I think you could make an argument that there might be, but most people argue there's none. So this has led to an argument that maybe chromatites are concentrated more at 3.5 to 3.2 and not so much before. It could not actually. Yeah, the preservation bias might actually be a real strong issue in making any determinations that way.
I thought it might change the model. We're always saying plate for push, that maybe somebody wrote some paper about maybe the pulling of plate. That's more important.
Well, I mean, of course, we're arguing for a single plate, single really hot plate that is moving at plate tectonic velocities vertically, just descending in a single plate that is having things move down at nearly, well, for Earth, not quite plate tectonic velocities, except for very early, but EO, plate tectonic velocities now as a descent velocity.
Yeah, so that's the old and cold.
Yeah, that's the old and cold flooding down.
Anyone else?
Somebody has something there.
It says, is there a geochemical composition variation of erupted materials with time according to heat pipeline?
Only to the extent that, you know, maybe if we drilled to that level, which we haven't in our modeling, then, by the way, I don't know if you can hear me. If you think about the volume production, the earlier hotter plant is melting larger percentages of the mantle, which probably means that the produced volcanics are closer to mantle composition. And the more you're melting, the less you're melting, the more the differentiation of that melt is a stronger difference from the original composition as a general rule. But you know, there may be caveats to that totally rule out the predicted observation there. And I wouldn't know them.
Okay. No more questions? Thanks, Alex.
Thank you. Thanks, guys. Oh, 4 o'clock, soonish. Yeah, sorry.
Yeah, I guess there's the SDR.
At around 5, yeah.
So if they're interested in having Alex take those here.
Thanks for coming.